Our senses are brilliant tools for survival, but not necessarily tools for understanding the true nature of reality. For millions of years, they taught us that the world is exactly as we perceive it, that galaxies, planets, atoms, and we ourselves move across a grand stage of space-time. And this conviction works brilliantly. It lets us catch a ball, drive a car, build houses, and send missions into space. But modern theoretical physics has begun whispering something deeply uncomfortable into our ear. What if that three-dimensional depth we treat as the foundation of reality is only a side effect of something deeper? What if space is not the fundamental stage on which physics plays out, but rather an image generated from information encoded somewhere else? What if our entire universe, from the most distant galaxies to the atoms in our bodies, resembles a gigantic hologram? This is one of the most fascinating, generative, and mathematically serious ideas in contemporary physics: the holographic principle. Imagine an ordinary hologram on a credit card. You tilt it at just the right angle, and suddenly you see a three-dimensional image. Something appears to protrude above the surface, or hide within it. You have the sensation of depth. You can almost peek around the corner of that image, but when you run your finger across it, you feel only flat foil. All the information needed to create the illusion of three-dimensionality is encoded on a two-dimensional surface. The depth you see is not a separate entity. It is an effect of the way information was encoded and read. And now comes the question that sounds almost absurd. What if the universe works the same way? What if the three-dimensional space we inhabit is a projection of information recorded on some distant boundary? What if matter, gravity, and perhaps even space itself are secondary to something more fundamental: information? That is the heart of the holographic principle. To be clear, it does not say we live inside a computer simulation. It does not say that some cosmic programmer booted up our world on an unimaginably powerful machine. It says something perhaps even stranger: that the laws of nature may be structured in such a way that a complete description of what happens in a given region of space can be encoded on its boundary. In other words, what appears to be a three-dimensional world may have a deeper two-dimensional description. But science did not stumble onto this idea because someone stared too long at a credit card hologram. Trail leads to some of the most extreme objects in the universe: black holes. For a long time, we imagined black holes as cosmic garbage disposals, objects so dense and so gravitationally powerful that anything crossing their event horizon disappears forever. Even light cannot escape. To an outside observer, a black hole looks like an absolute trap. But in the 1970s, Jacob Bekenstein and Stephen Hawking discovered something that completely changed the way we think about black holes. It turned out that black holes have entropy, and entropy, put very simply, is connected to the amount of information that can be assigned to a given system. If we have a gas sealed in a box, the larger the box, the more particles it can contain, and the more possible states the system can have. In the ordinary world, information scales with volume. Bigger box, more room for data. But black holes behave differently. Bekenstein noticed that the entropy of a black hole is not proportional to its volume, but to the surface area of its event horizon, to that boundary beyond which there is no return. It's as if you wanted to know how many books fit in a library, but instead of measuring its interior from floor to ceiling, you had to count the bricks on the outside walls. or as if the capacity of a hard drive depended not on what was inside it, but solely on the surface area of its casing. It was completely counterintuitive. The black hole seemed to be telling physics, if you want to know how much information fits in a region of space, don't look at the volume, look at the surface. From this was born the Beaconstein bound, the idea that there is a maximum amount of information that can be packed into a finite region of space, and that this amount is tied to the area of the region's boundary, not its volume. This was the first strong signal that three-dimensional space might be, in some sense, redundant, that nature may not need to write everything into the volume. Perhaps the surface is enough. But the real drama was only just beginning. Stephen Hawking showed that black holes are not completely black. For quantum reasons, they can emit radiation. They very slowly lose energy, and over an extraordinarily long timescale, they can evaporate entirely. And this is where the famous black hole information paradox appears. Imagine throwing an encyclopedia into a black hole, or a computer, or the entire archive of human civilization. According to quantum mechanics, information about the state of a system should not simply vanish. Quantum evolution should be unitary, in principle reversible, and information should not be destroyed. But if a black hole swallows matter, and then evaporates in the form of radiation that at first glance does not carry the full information about what fell in, then where did that information go? Was it truly destroyed? If so, quantum mechanics would face a profound crisis, a problem lying at the very foundations of physics. The solution proposed by, among others, Gerard T. Hooft and Leonard Susskind was radical. Perhaps the information about what falls into a black hole is not stored in its interior the way we imagine. Perhaps it gets encoded on the event horizon, on the surface of the black hole. From the perspective of an outside observer, an object falling into a black hole never simply vanishes into the interior. It becomes smeared, stretched, and written onto the horizon, like information on the surface of a cosmic hard drive. The black hole began to look like a natural hologram. Its three-dimensional interior could be described by information encoded on a two-dimensional boundary. And then came an even larger, even harder question. If a black hole works like a hologram, could the entire universe work the same way? The breakthrough came in 1997, when Juan Meldacena proposed one of the most important ideas in modern theoretical physics, the ADS/CFT correspondence. It sounds highly technical, but its meaning is genuinely fascinating. Meldacena showed that a certain kind of space containing gravity, so-called anti-de Sitter space, the ADS part, can be described by a completely different theory operating on its boundary. Inside, we have space with gravity. On the boundary, we have a quantum theory without gravity. And yet, both descriptions are mathematically equivalent. It's as though we had two completely different languages describing the same reality. In one language you speak of gravity, black holes, curved spacetime. In the other, you speak of quantum fields on a boundary where gravity does not exist at all. And yet both languages describe exactly the same physics. You can compare it to a vinyl record and the music filling a room. The record is flat, covered in grooves, and yet when the needle reads the inscription, we hear space, depth, instruments, voices, dynamics. What sounds like a three-dimensional experience is ultimately encoded on a surface. In Meldacena's correspondence, something similar happens with physics. What inside looks like a space with gravity can be described on the boundary as a purely quantum system without gravity. This was a great aha moment for theoretical physics, because if gravity appears in one description and is absent in the other, then maybe gravity is not fundamental. Maybe it is an emergent phenomenon, something that arises from deeper quantum structures. And if gravity can emerge, maybe space itself is not the foundation either. Maybe space is not the empty stage on which physics plays out. Maybe space is an effect of physics, a byproduct of information, correlations, and quantum entanglement. And this is where one of the most astonishing chapters of this story begins. In recent years, physicists, among them Mark van Ramsdam, have begun to show that the geometry of space-time may be deeply connected to quantum entanglement. Entanglement is one of the most remarkable phenomena in quantum mechanics. Two systems can be described by a shared state in such a way that they can no longer be treated as fully independent, even when they are far apart. In popular language, people often say that the state of one particle instantly affects the other. But we must be careful here. Entanglement does not allow information to travel faster than light. It is not a cosmic internet without delay. It is a deep correlation between elements of a system, one that eludes classical intuition. In holographic models, entanglement may play the role of threads from which space itself is woven. Regions that are strongly entangled are, in a sense, close to each other in geometry. If we reduce the entanglement between parts of a system, the corresponding space may stretch, separate, and in extreme cases, even break apart into disconnected fragments. It sounds like pure abstraction, but it carries deep meaning. Space may be a map of informational relationships, not something primordial, but something that arises from a network of quantum connections. Completing this vision is the ER equals EPR conjecture, proposed by Meldesena and Leonard Susskind. The name looks like a mathematical incantation, but it conceals a rather beautiful idea. EPR refers to quantum entanglement from the names Einstein, Podolsky, and Rosen. ER refers to Einstein-Rosen bridges, the space-time tunnels you almost certainly know as wormholes. The ER equals EPR conjecture suggests that quantum entanglement and the geometry of space-time tunnels may be two descriptions of the same deeper reality. This is not saying that every pair of entangled particles creates a tunnel you could fly a spaceship through. Absolutely not. This is not a shortcut to the Andromeda Galaxy. Rather, the idea is that entanglement may have a geometric counterpart, that quantum correlations and the structure of space may be different sides of the same coin. In this vision, space-time is not so much a stage, as a fabric sewn from those very relationships, and the thread of that fabric is quantum information. This shifts our intuition about reality into a completely new place. For centuries, we thought the foundation of the world was matter. Then physics showed that matter is a form of energy, and particles are excitations of fields. Now, increasingly, the thought arises that even deeper may lie: information. John Archibald Wheeler captured this in the famous phrase, "It from bit." The idea that physical phenomena may have an informational structure at their foundation. Today, some physicists go further and speak of it from qubit, because if we are talking about the most fundamental level of reality, classical zeros and ones are no longer sufficient. We need quantum information, entanglement, and superposition. In this picture, the world is not built of tiny balls of matter flying through a void. It is rather a gigantic, dynamic process of information processing. And space, time, and gravity may be the way that process looks from the inside. And speaking of time, if space can be emergent, what about time? Here we enter even more speculative territory, but the direction of research is fascinating. Some models suggest that time, too, may not be a fundamental ingredient of reality. It may be connected to change, the growth of complexity, the ordering of information, or the way quantum systems evolve relative to one another. This does not mean, of course, that time does not exist in any ordinary sense. For us, it exists absolutely. We age, we remember the past, we do not remember the future. Most of us, anyway. We plan, we wait, we run late. We suffer and we grow, in time. But from the perspective of fundamental physics, time may be something like temperature. Temperature is real when we talk about a gas, a cup of tea, or a planetary atmosphere. But at the level of a single particle, it is no longer such a basic concept. It emerges only from the collective behavior of vast numbers of elements. Perhaps time works similarly. Perhaps what we experience as the passage of time is, at a deeper level, simply the changing structure of information. All of this sounds extraordinary, but science cannot stop at elegant mathematics and beautiful metaphors. We need contact with reality. We need observations, experiments, some trace. And this is where the harder part begins. The holographic principle is enormously powerful in mathematics, particularly in the context of ADS/CFT. Problem is that anti-de Sitter space is not exactly our universe. Our cosmos, as far as we know, is expanding ever faster and more closely resembles a space with a positive cosmological constant, not a negative one. This is a very important caveat. We cannot simply say, Meldasena proved we live in a hologram. No, that would be a vast overstatement. Meldasena showed that in a certain very important, mathematically precise model, holographic equivalence works. That is a tremendous theoretical achievement. But carrying that idea over to our actual universe remains one of the great challenges of physics. There have also been attempts to find experimental traces of a holographic structure. One of the most well-known was the Fermilab holometer, an experiment designed to search for so-called holographic noise, tiny fluctuations resulting from a possible finite resolution of space-time. Because if we are talking about a holographic encoding, there should be some resolution. The results did not confirm the existence of such noise in the range studied, but this did not refute the holographic principle. Many physicists felt that true holography need not manifest itself as simply as graininess in an image on a screen. This matters because it is easy to fall into overly literal analogies here. If the universe has a holographic description, that does not mean that at sufficient magnification we will see pixels, like on an old monitor. Planck's scale may define the limits of our current concepts of space and time, but it need not mean simple geometric building blocks from which reality is constructed. Equally important are cosmological studies, attempts to apply holographic ideas to the very early universe, to inflation, to the cosmic microwave background, and to the birth of space-time itself. Some holographic models can reproduce certain features of the cosmos in ways that compete with classical descriptions. But here again, we must speak with care. These are promising directions of research, not yet a delivered verdict. And that caution is precisely what makes this story beautiful. The holographic principle is not just cheap sensationalism. Scientists prove the world is an illusion, scratching their heads, and so on. It is something far more interesting. It shows that our most basic concepts, space, volume, interior, exterior, distance, may be only approximations. They may work beautifully at the scale of our experience, but they may not be the final word in physics. This has already happened many times before. Once it seemed obvious that the Earth was the center of the world. Then it turned out to be a planet orbiting the sun. Once time seemed absolute. Then Einstein showed it depends on motion and gravity. Once matter seemed concrete and continuous. Then quantum mechanics revealed that at a deeper level, reality is probabilistic, strange, described by wave functions, and most likely simply an emanation of energy. Now perhaps we stand before the next shift. Maybe space is not the container in which information exists. Maybe space is what information does when it arranges itself in a sufficiently complex way. It is also worth distinguishing the holographic principle from the simulation hypothesis, because they can seem similar, and the two are often confused in popular culture. The simulation hypothesis says our world could be a program run by some external civilization or a higher level of reality. That is more of a philosophical question, though sometimes dressed in the language of technology. The holographic principle needs no external computer, no programmer, no real world in quotation marks beyond our own. It does not say someone is simulating us. It says the laws of physics may have a structure in which a complete description of a volume is equivalent to a description on its boundary. This is not the matrix. It is a hint that nature itself may be more informational than we ever suspected. So, what does all of this say about us? We must be careful not to drift too far. The holographic principle does not prove that consciousness creates the universe. It does not prove that thoughts change reality, or that the cosmos is some kind of great mind. Those are serious distortions. But it does change the context in which we think about ourselves. If information is truly one of the deepest currencies of physics, then we, as beings who process information, remember, observe, build models of the world, and ask questions about its structure, are a remarkable phenomenon within this cosmic process. Not because we stand apart from nature for some reason, but precisely because we are part of it. We are a fragment of the universe that has learned to look at itself and ask, what am I made of? And the answer may be stranger than we assumed. Perhaps not only atoms, perhaps a certain kind of relationship, of correlations, of entanglement, of information. If so, the picture of reality changes radically. We are no longer lonely lumps of matter in space, but local patterns in an immense network of dependencies. Part of a structure in which what we call here and there, inside and outside, surface and depth, may be only our way of reading a far deeper code. But none of this takes away the reality of our lives. If reality has a holographic description, that does not mean that pain, love, joy, and fear, that our choices, are false. A hologram on a credit card is flat, yes, but the image you see is still a real optical phenomenon. Temperature may be emergent, but a scalding cup of tea, well, it will genuinely burn you. Perhaps we are the same. Even if the space we live in emerges from deeper informational laws, our experience remains real at its own level of description. Science does not strip meaning from the world in this way. It only changes the depth at which that meaning is understood. The holographic principle is therefore something more than a strange theory about black holes. It is one of the most daring attempts to answer the question, what exactly is reality? Is space fundamental? Is gravity a basic force, or an effect of something deeper? Can information be more primordial than matter? Is the universe something that exists in space? Or is space the way the universe organizes information? For now, we do not have the final answer. Perhaps the holographic principle, in its strongest form, does not precisely describe our cosmos. Perhaps it will prove to be only a brilliant mathematical tool that works in special models, but is not a complete theory of reality. Or perhaps future physics will show that it was one of the first glimpses of a new paradigm, one in which space, time, and gravity emerge from quantum information. Either way, its impact on science is already enormous. It forced physicists to rethink black holes. It gave new tools for studying quantum gravity. It united information theory, quantum mechanics, and geometry into one of the most elegant pictures in modern science. And for us, ordinary people gazing up at the night sky, it offers something more. It reminds us that reality need not be as our intuition suggests. We look at the world and see solid, hard objects, space, distance, depth. But perhaps underneath lies the most complex cipher that has ever existed. A cipher in which a surface can contain an interior, information can give birth to geometry, and a boundary can describe an entire cosmos. Perhaps, then, the greatest journey is not a journey to the farthest galaxies. Perhaps the greatest journey is the attempt to understand why there is space to travel through it all. Because if the universe truly has a holographic structure, then what we took to be the horizon of knowledge may be only a surface, and encoded within it is the entire secret of that depth.